Hello everyone, my name is Shelva. I am representing my today topic on B-tree in advanced data structure. So as we know, this is a very good approach if you would like to do the proficient and we can say the efficient utilization of memory, or rather we can say if I would like to sort the data efficiently, this approach helps a lot. Let us start now. Yes, do the beginning from a very well basic introduction about B-tree. As we can see, this is known as high balanced M-way search tree. So as we can see here, the term has been given, that is M-way search tree. So what does it mean, M-way search tree? So M means order. So now what does it mean, order? It means that the number of data elements having provided to me, I have to sort that data element in efficient way by selecting some algorithmic approach of B-tree. So we having some basic introduction about it. Let us discuss that. A B-tree is a special kind of tree in data structure. In 1972, this method was first introduced by McRae and Baird named it as high balanced M-way search tree. As we know that a very good keyword also comes here, that is the balanced. What does it mean, balanced? Balanced means the data element when I am going to sort in this efficient data structure, it is going to be sorted in a perfect order. So how I can explain this? What does it mean, perfect order? Through some approaches, and I can say having the operation of B-tree, by applying that operations in such data items, I can understand the topic in detail. So now I would like to tell you that it helps us to preserve data sorted and allowed various operations like insertion, searching and deletion in less time. So this is obvious approach that we always like to afford such technology to arrange the data set, and we can say we would like to opt such technology which perform very good task in very lesser interval of time, so that I can prevent my performance issues. I would like to resolve the performance issue if I am going to utilize my processor in efficient way. So I would like to reduce the idle time of processor. That is ultimately what I would like to say. So this B-tree efficiently work with this less time approach. B-tree is a specialized M-tree data structure exists with order M and also can have at most M-1 keys. So what does it mean? The number of data elements which we having here, if I would like to say what is key is generally nothing but it corresponds to the data element. So always key always having one less number as compared to the order. So that's why it has been given here M-1 key and M children. So one good advantage of B-tree is that it is very efficient as compared to BST. Yes, I can say that B-tree is following the approach of BST tree for arranging the data elements, right? But yes, in B-tree, I also having one advantage where I can arrange my data structure by collecting n number of children. Rather, in BST, only I having the two children, either on the left side of subtree, either on the right side of subtree. Continue further. Properties of B-tree. Yes, I having here a very interesting topic to introduce with you all. That is all about the properties of B-trees. So what does these properties make themselves unique as compared to the rest of the strategy of the data structure? First of all, I would like to say, yes, we know that B-tree is a very integral part of our advanced data structure. So yes, now we have to proceed with the properties. Like as first it has been mentioned here, the B tree is NV tree. As I said you that NV tree means here we having the n number of children and the order also vary as per the different level. But one thing we have to keep in mind that the level of leaf node always will remain the same. There is no distortion should be there, and I can say if there is no parallelism in the leaf node, it means this bead structure is not perfectly performed. So yes, this B tree is balanced MV tree. This is generalization of BST, as I said before, that BST is a binary search tree, and binary search tree only we having the two children either on the left and either on the right hand side. But here this is an exploration of a BST, which is a part of our B tree. And in this node have more than one keys and more than two children. As I said before, B tree is not a binary tree because here construction of tree depend on n. It maintains the sorted data. Yes, again this is a very important thing to understand that in B tree we have to keep one thing in mind, that when I would like to apply the strategy of B tree on my data elements, I have to keep one thing in mind that always my data elements are in sorting order. All leaf node must be at the same level. Again, the very important point we have to follow. Now, I would like to tell you about the structure of B tree nodes. Yes, nodes consist the data elements, right? And we can say the information set is available inside the nodes or the values. Here, in this representation, I can say I have here the n number of children with n number of children, and I having here the number of keys. As through this diagrammatic representation, this is very clear. The number of keys are very one less as compared to the number of child node. We can see here perfectly. In this, suppose I have taken 5 keys. Let us say K1, K2, K3, K4, K5. In this, what we having, the number of child nodes are always in increased order as compared to the selected number of keys. So that's why we are saying that number of keys K is equal to m minus 1. So the order, that is the number of children, always remain higher as compared to the number of keys. Now we having the calculation of nodes. Yes, why we have to continue this with the calculation of nodes, because we say again and again that we have to do the proper sorting of data elements, right? So these methodology we have to opt for the perfect sorting of data elements. So as we can see here, B tree of order M have the following properties, like as every node has maximum m number of children, as we have shown here in previous slide. Here we having the 6 children, and here I having the 5 number of keys. So the similar has been mentioned here that every node has a maximum m children. Here we can see we having the leaf node. The leaf node having children 0. What does it mean? Leaf node always we having the very final stage, means after leaf node do not having any child basically. So that's why it is pointing to the 0, means there is no children for the leaf node. Then we having for root node, minimum children are 2. Then if I am talking about the internal node, then how the children are going to be counted for the internal node by applying the formula m by 2. So what does it mean? Now, let us say I have in here, this is my root node, and these are the number of child. Let us say C1, C2, C3 and C4. And yes, again I have the leaf nodes. Let us say I have the leaf node here. So now what we understand by the term internal node. Internal node means the middle stage of our data structure, the middle part of our data structure, where overall combination of nodes is going to be made. For example, internal nodes are basically the area in between the root node and the leaf node, I can say. Yes. So internal node, number of children who corresponds to the internal node. If I would like to count, I will apply the formula n by 2. Every node has maximum n minus 1 number of keys. This is obvious. And now how to calculate the main keys, that is the minimum number of keys. For root node, always the keys will remain, minimum count of keys always remain 1. For all other node except the root node, we having the number of keys which we can calculate by using formula m by 2 minus 1. Now, insertion of values always would be at the leaf node. This is a very important point to understand, that always if I would like to insert a data element in this B tree data structure, I have to follow the insertion from the leaf node. But yes, when I have to visualize the approach of my data structure or the node inside this B tree data structure, then I come to know that from the root node I have to check the alignment up till the leaf node, and yes, insertion going to be occurred from the leaf node. Now here very important operations of B tree has been discussed. First is the insertion and the second one is integration. Yes, as we know, without algorithm, there is no mean to proceed how the data elements are going to be arranged and how the order is going to be visualized and checked. So the basic steps, first of all, we have to follow. So algorithmic approach gives us the strategy how to achieve the objective, right? So here, algorithm for insertion operation, we are having some points here. The very first has been given: traverse the B tree to find a location at the leaf node to insert the item. Yes, we have to do the traversing. What does it mean, traverse? It means that we have to explore each and every node inside the given data structure unless we have been achieving our targeted node to insert the data element in that. So as we know earlier, leaf node is that part which we have to identify for the insertion of data element. Yes. Second point, if the leaf node contains the keys which are less than n minus 1, then insert a node in increasing order. So if this condition occurs, then always we have to do the insertion operation in increasing order. Let's go further. Now few other condition also has been occurred here which we have to study. Second condition is, if the leaf node, the keys of leaf node is equal to n minus 1, then what the sub conditions generated, we are going to be studying all these through these conditional statements. Insert a new item in an increasing number of items. Take the median of the nodes and split the node into two nodes. Next, push median to its parent node. Second, if parent node key is equal to n minus 1, then repeat the above step for parent node as well. This is done until we find the appropriate leaf node. Finally, then we will insert the element. So now, how these all steps actually are going to be implemented on the example? These all we are going to be understand with the help of the example which I have taken here in these slides. So yes, working of insertion operation. So first of all, I would like to say, yes, algorithm we already have studied. These same steps are now I have to follow. to insert the data element in the given data structure, or I can say if I have to make a perfect B tree, then what steps should I follow? So such steps I have discussed earlier in the previous slide, where we have discussed about the algorithm. So now let us say insertion. I would like, this is the one example which I have selected to explain the insertion operation. Let us say we have in the problem statement, we have to create a B tree of order 3 by inserting value from 1 to 10. So what has been given here basically? Here the order m is given, that is equal to 3. So yes, the beginning of my the understanding, or I can say the analysis to solve the problem, yes, start from this point. Here, as I come to know, if order has been given, if let us say m is equal to 3, then I have to start with this. What is here mentioned? If m is equal to 3, then I have to compile what different terms should I calculate now. That is the maximum child, the minimum child, the maximum keys and the minimum keys. These all things we have already discussed by using some basic terminology in the previous slides. So yes, here let us say I having m is equal to 3, the given problem statement I have to solve. Here the max child is 3, and what are the key? That is m minus 1. So what it would be? 3 minus 1, that is equal to 2. So the maximum keys for this particular problem statement must having the order 2. So yes, now continue with this. Insertion in B tree always would be in sorted order, which is obvious, and because we generally relate this B tree with the balanced search tree, so that is how this term, that is the sorted order, should be maintained during the solving nature of this problem statement. Now next we having the new value always inserted from the leaf node. So this is how this particular problem is going to be analyzed first. Now we have to solve it. First of all, I will start with the insert operation. As we know that we have in the numbers from 1 to 10, and from 1 to 10 in sequential order, in perfect order, I have to sort all the data elements. And what strategy should I follow if I having the m is equal to 2, and if I having m is equal to 3 and the number of keys is equal to 2. So this is obvious, where the 3 keys are going to be generated, the splitting rightly is going to be dwelled from that part, and I have to do the proper balancing of the tree. Let's start with it. The problem statement is clear to us. From 1 to 10, we have to maintain the order, and in that way we have to make a perfect B tree. So let us start from very first step. First of all, we will insert 1 and 2. Why we are taking simultaneously 1 and 2? Because this is obvious. If 2 keys I can select, so 2 data elements I can insert. Second step, insert 3 by splitting the middle element. Yes, what does it mean? 3. When I am going to be insert 3, in 4th step, I have to know my somewhere the sequence is going to be imbalanced. How? Because only the 2 keys are going to be opted by this strategy. So here is the point from where the splitting is going to be counted. Third step, as I discussed before, the splitting is going to be performed here. Yes, to do the arrangement of the node in this B tree data structure, we have to follow the BST strategy. Somehow we also know that BST and B tree have no similarity, but yes, to arrange the data element perfectly, few of the property of BST we have to opt. So here, as we know, the left node of this particular arrangement would be lesser as that of the root, and the right side of node always having the data item greater as compared to the root node. So this is how the arrangement we have to keep in mind. Fourth step, insert 4 now in the root node. So yes, I having here, I can insert here the 4. How I can insert it? Yes, 4 is greater than 2 and perfectly the order is going to be maintained here. So this is the way where I can insert 4 in this particular arrangement, and this is how the order is maintained. And now my next element would be 5. Again, 5 will come here. When I am going to insert the 5, again the arrangement of 3 keys are going to be made here, which is again not going to support the balanced strategy of this B tree. Again, this splitting is going to be performed. So this is how here when the 5 and 6 is going to be inserted in this given B tree, which we would like to solve in the given problem statement of arrangement. The data elements from 1 to 10, as I come to know that, here is how the 5 and 6 is going to be inserted. Because I have the provision that I have the 2 keys, I can balance 2 keys location here. So I did the same here. In 6 step, what I have to do, I have to insert the 7 and 8. Yes, again, if I would like to insert 7 in this first step, I come to know again the imbalancing is going to be performed, right? So how it is going to be occur? This is how we have come across in the algorithm. Here, when I am going to be insert 7, so what happened? If I am going to be insert here the 7, again the imbalancing nature is going to be occur. So splitting I have to perform. When I have to perform the splitting, what happened? When the 7 is going to become here, let us say 7 is going to become here, we know that key is only going to be supported, that is 2, right? So what is, how I can make the balance here? This is obvious. Middle element is going to be moved to the upper side, right? So when the upper side movement is going to be take place, again we have to search for the location. Is there any vacant space or not? Yes, there is no vacant space. So what is going to be happening? Again, 6 from here is going to be moved to this side. So now 2, 4, 6. This order is going to be performed. So splitting is going to be occur. So splitting is going to be occur. Then we know that from 4, this side the 2 will come, this side the 6 will come. So the same strategy has been opted here to come to the left side of this node, and 6 comes to the right side of this node, because this is the perfect balancing is going to be performed. So this is how the arrangement of 7 and 8 node is going to be occur in this particular example. Now come to the further part. Yes, in 7th step, what I have to do, I have to insert 9 and 10. Yes, I am having here the strategy, or I can say I am having the perfect space where I can insert directly 9 and 10 without making any rearrangement and all, right? So here what is happened, 9 and 10, again I have going to be inserted here in the leaf node. Again, the main very important point is that whensoever the insertion is going to be happen, always it is going to be made in the leaf node only. So that is how, and yes, how this BS tree is balanced tree. As you can see, all the leaf nodes are in the perfect same order, and the level of all these leaf nodes again are same. So this is how the problem statement of insertion is going to be solved. So this is how insertion works. Study. Now come to the next, that is the deletion algorithm. Yes, when we are going to be discussed about the insertion, yes, we also have to free the memory space, because this is not always happening that only we have to insert the data. Sometimes the strategy of deletion we also have to opt, and we also utilize the memory spacing well order. So this is how the deletion algorithm work in in this B tree. First of all, we will locate the leaf node. In case the number of key in a node is greater than m by 2. As I told you before that m by 2 generally we recall to calculate the number of child which are available inside the internal node. nodes. So always the ceiling we are going to be opted here. As per that, we come to know these are the number of keys are going to be counted in the internal nodes of our given B tree. So in case number of key in a node is greater than n by 2, then delete the given key from the node. If such condition is going to be happen, we directly going to be delete the number of the given target key from that given structure. So this is what that if my perfect order is going to be work there, if highest keys, if I am going to be select, directly I can delete the element from there without searching for the left and without searching from the right arrangements. Okay. In case the leaf node is not having n by 2 keys, what does it mean? If we having lesser number of keys from the maximum number of keys, then somehow we have to make the proper balancing factor again. So now how the balancing is going to be made here? So in case the leaf node is not having n by 2 keys, then we need to complete the keys by taking keys from the right or left subtree to maintain the B tree. Yes, here is the point which we need to understand. What I said, we having, let's say I having the maximum number of keys, let us say that is 2, right? So if having the maximum number of keys that is 3, directly I can delete the data element from there. But let us say I am having the minimum number of key that is suppose 2. So now if such situation going to be occur that I can't opt the 1, if I am going to be opt the 1, then again the imbalancing is going to be performed. So what strategy I have to maintain so that the order of 2 in sense of keys are going to be maintained. So somehow I have to pick few of the condition from the left hand side of subtree. Somehow the situation can also be there that I have to pick the data element from the right hand side. If the right subtree contains n by 2 elements, then we push its smallest element to the parent node and then move the intervening element to the place where keys was deleted. So this is our third condition. If no node has n by 2 elements, then the above steps cannot be performed. Thus we create a new leaf node by joining 2 leaf nodes and the intervening element of the parent node. What does it mean? Somehow the situation is going to be performed that on the both sides we having a very perfect balancing, but somehow suppose I would like to distort that balancing because I would like to delete the data element from that location. So somehow what I have to opt with the strategy that is the merging. So in that case, when I do not have a situation or a solution in front of me, I need to delete the element. In same time also the order somehow is also going to be distorted. Again only the one solution in front of me, that is in terms of merging. So I will merge all the nodes by selecting its parent node. So this is how all the deletion different cases are going to be worked. So yes, here is working of deletion operation. Deletion occur in 2 ways. So in this particular lecture I am going to be focused especially on the leaf node case, and the internal node case I am not going to be discussed here. So this is obvious 2 cases of deletion generally occur inside the B trees. So let us say I am having the order m that is equal to 5. So what is the number of key? Obvious m minus 1, that would be 4. So what is the minimum children? Minimum children always we having by n by 2, that is equal to 3. Main keys is equal to 2, max key is equal to 4. These are the formulas, these are the strategy with the help of which we can calculate the max, min child, min keys and the maximum number of keys. Yes, working of deletion operation. So let us say I would like to perform some deletion operation. So how I would like to opt with this. So yes, you can see here this is the BST tree, and somehow I would like to remove the nodes from here. Let us say I would like to delete the 64 from here, from this location. Then what I have to go with which strategy I have to select. For this, what I will do first of all, I will check my neighbor nodes first of all, right? So I can make some arrangement with that or not, right? Let us say, for example, if I am going to remove 64 from here, then which strategy I can follow so that my balancing also is not going to be disturbed, because 64 directly I can't remove from here. So I am having few methodology here. From here we come to know that how the nodes are going to be deleted and which strategy we have to follow in upcoming slides. So these are the cases. In detail I am going to be discuss all these. The first case would be when I would like to delete the 64 from the given tree, and then 23 and then 72. So these are very common things to do, but yes, the strategy which we are going to be opt here are very different. Suppose first example I am taking, I am deleting 64. So what I am going to be taking this is going to become under the case when leaf node contain more than minimum number of keys. So this case is going to be opt with that. Second, if leaf node contain minimum number of keys, then what is going to be happen? For that I am going to be select the deletion of 23 operation. Then the few cases are going to be dual. First, borrow from immediate left node or sibling through parent node, borrow from immediate right node or sibling through parent node. So means the involvement of parent node for the rearrangement is very mandatory. A third case also developed when if neither left sibling or right sibling having more than minimum number of keys, then merging operation will perform. Now how these all works? Yes, first of all, working of deletion operation is going to be happen here. For example, I am going to be delete here 23 from the leaf node, borrow from the immediate left leaf node. What does it mean? This is the case which I am going to be solve this particular problem, that is the deletion of 23. So as you can see here, we will always traverse all the given data structure through from the root node first, right? So as I come to know that where the 23 already exists, so I am going to be searched there. So yes, I am going to identify that my 23 is present here on this leaf node. So yes, which strategy I have to follow? Borrow from the immediate left leaf node. Yes, why I need to take here the borrow? Because I know that only my two data elements can make the arrangement possible if my one single element is going to be inserted in this and one remain without data elements, then somehow the imbalancing is going to be performed. So this is how the minimum number of keys should be there in the B tree, that is 2, and the maximum number of keys should be, that is 3. So now this is okay when I am going to do the arrangement from 3 to 2, but if I am having less than 2, then the imbalancing somehow is going to be come. Now again, this is our left side, right? And what is going to be understand how I can understand this? If I am going to be relate all these structure with my left part of this tree, if I am going to compare with the root node, then I come to know that this 23 generally lie to the left side when I am generally talking about the root node, right? So specifically inside the intermediate nodes, when I come to know the further crossing about this leaf node, then I come to know 23 is here. I directly can't do the deletion of 23. So what I would do? So I will do what? Borrow from the immediate leaf node. So what is going to be happen? The maximum number. The maximum number is going to be shuffled from here to the upper node. So this is how the 16 is going to be come here, and after this 20 is going to be come here, and then 23 is going to be deleted. So this is how the strategy is going to be performed if we would like to do the rearrangement of nodes. So after this I come to know that this is how all the deletion of nodes is going to be happen. Now borrow from immediate right node or sibling through the parent node. Now the second case I would like to discuss here, when there is the need to opt the immediate right node. What will such case is going to be happen? Suppose here I would like to say that I have to delete the 72, right? So in my this slide you can see here the 72 is here somewhere else. Now I would like to delete this. When I would like to delete this, so what happened? The single entity is going to be, single number is going to be maintained here, which is not again opting with the minimum number of keys, right? So again the imbalancing is going to be performed. So what the strategy I should have to follow? You can see here I can't borrow from the left side. Why? Because here already I am having the two data elements, so I do not have any provision to opt the data element from here. Means from the left side. So what I am supposed to do? I will take borrow from the right side, right? So this is how the shuffling and the rearrangement is going to be happen. So in next slide, this all come to know. Yes, when 72 is going to be deleted in this node that was presented previously, so now that is going to be deleted by opting the strategy of borrowing the data element from the right node. So what happened? The minimum number of data element is going to be moved to the upper node, and then from there the again the rearrangement is going to be happening. Suppose let us say in this slide we can have here this I would like to delete, and from here what I would like to do, the minimum number of element I would like to move further. So what I am having with 77. So 77 will move from here to here. So now from here again we have to make some shuffling. So rearrangement we have to do. So 75 now will move from this node to the leaf node, and then 72 is going to be deleted. So this is how second case works when I am having the provision to take the borrow from the right hand side, then what is going to be happening, right? So we can see 72 is going to be omitted. Now we have the data element that is 73 and 75. So this is one example of this. Now what is going to become further? That is the third case we have it. If neither left sibling or now the third case we have, if neither left sibling or right sibling having more than minimum number of keys, then what is going to be happening? So what does it mean? Suppose I am having the case. For example, this is my root node, right? And again I am having some child from this node. Let us say. Now what we having? This side again I having the minimum number of key, and this side also having the minimum number of keys. Now the question is, I would like to delete the data elements from the already balanced set. So what is going to be happen in that case if I would like to do the distorting of this? So this is the case, only the one solution with this, that is we have to opt the merging operation for such type of problem. So this is how the problem is going to be solved. Now come to the next. We can say after deletion of 65, this is the final output of B tree which is going to be come. So now what is going to be happen? Yes, 51, 52, 65, 60 and 68 is going to be merged here. So ultimately what I would like to explain here, I have to delete from here the data element 65. Now when we have to delete the data element from the given structure, then what we have to do? First of all we have to follow the analysis, right? So should I have the provision that I can take borrow from the left side? Should I have provision that I can take borrow from the right side? Yes, if we have it, then the previous discussed two strategies we can opt. But yes, if we do not have a provision, that neither we can opt the borrow from the right, neither we can opt borrow from the left side, then only we having the solution that is merge. What does it mean now? So yes, Merging, ultimately we know that when we are going to be combine more than two sections together, right? So ultimately this node I would like to delete, right? So if I would like to delete this, the single element is going to be placed here only. So this is again imbalancing is going to be occurred, right? So what is the solution now? Having that my perfect order is going to be maintained. First of all, what I would like to say, I am going to be merge these two nodes, right? So when I am going to be merge these two nodes, always keep in mind that the involvement of my this root node is very important, because without involvement of my root node I would not be able to make a direct merging in this. So after this overall arrangement, I come to know that few particular data structure of B tree data structure is going to be performed here. That is, we can here we have a image in front of us. We are having two elements, 70, 77, and it's we having the three child, right? And again the perfect balancing is going to be maintained here. 70 on the right hand side we can see we having the larger number of value, and on the left hand side we having the lesser number of values to the root node. Similarly, with the case of 77, if I am going to do the comparison with 70 and 79, perfectly I can see that 70 and 79 having the larger values, or these are larger values as compared to 77, as these are going to be maintained on the right hand side of the given tree. This is how the overall arrangement is going to be made when we have the case neither we having the left sibling or neither we having the right sibling to of the border. Now at the end, I would like to say we having the application of B tree. As I discussed before that for the perfect utilization of technology, we generally say that our processor never should be in idle state, right? And we also do not make our memory structure very harshly bulky, so that the unused files remain as it is in the memory space, and the over utilization of my memory is going to be take place over there. So I have to resolve all these shortcomings. So I again and again I can say B tree again having so many advanced strategy. If we are going to be opt such strategies with B tree, again few refinements going to be done. But yes, very shortly I am going to be discussed here the application that is, it is commonly used in database and file system to store and retrieve data in an efficient manner. So this is all about my today discussion, and the rest of the topic of which concern to B tree we are going to be discussed in upcoming video lecture. So have a nice day. Thank you.